Okay, so charges can be part of conjugated systems. Lone pairs, importantly, can also be part of conjugated systems. And so one of the ways that we introduce lone pairs into organic compounds is we use heteroatoms. And so this is kind of the last introductory video of this unit. The last one is going to be what happens when we have heteroatoms, and it won't surprise you to learn that heteroatoms basically add lone pairs. So here we go. Heteroatoms in aromaticity. Okay, so let's go back to our 5-membered rings because we can recall what those look like. So we had our anti-aromatic 5-membered ring that looked like this with the cation on it. When we have a lone pair at that carbon, we get an aromatic compound. And then when it was neutral, it was non-aromatic. So what happens, let's look at what happened, well, let's use nitrogen first. What happens when we put a nitrogen in this position? Now this nitrogen has a lone pair on it because neutral nitrogen has 3 bonds and 1 lone pair. Right, remember that from the first week of Organic 1. Now we've got a lone pair here. Is this compound aromatic or anti-aromatic? Well, do we have a complete conjugated system? The answer is yes, right? We can draw resonance forms where we make pi bonds at every atom that's in this molecule, right? So we can have that nitrogen be a part of a pi bond. And yes, that makes the nitrogen charged, but that's okay because charge is perfectly acceptable as part of an aromatic system, right? We saw that in the previous slide. And so complete cyclic conjugated system, you betcha. How many pi electrons do we have, right? Well, we can look at how many pi electrons are moving around in our resonance structure, right? We have 2 pi bonds, that's 4 pi electrons. We have 1 lone pair, 2 pi bonds plus 1 lone pair equals 6 pi electrons, right? And so this compound is aromatic, right? And so this compound is actually called pyrrole. It's a nice stable compound. It's not very reactive. The nitrogen on pyrrole is not a very reactive nitrogen because that lone pair is important for aromaticity. If we react the lone pair, then all of a sudden we end up with, we've broken the aromaticity, then there's no ring there, right? Or there's no cyclic conjugated system. All right, so nitrogen in that position makes it aromatic. What about oxygen? So this might be a little bit tricky. You might say, oh, we got 2 lone pairs here. I need to add both those lone pairs in here. But think about the resonance and remember that we only use 1 lone pair, right, to draw resonance forms of this. And so when we're counting the pi electrons, right, there's only 1 lone pair used in resonance. Right? So this is a potential stumbling point, right? So when we count this, we have 2 pi bonds, of course, that's 4 pi electrons, and we have 1 lone pair, because we're only going to count things that contribute to the resonance forms, right? So we only have this 1 lone pair that's in there, so if we draw the resonance form, we would use 1 lone pair, make a pi bond, etc. This all adds up to 6 pi electrons, and so the oxygen containing ring is also aromatic. So this is important. Oxygens in general only contribute 1 lone pair to resonance, right? We don't contribute both lone pairs because that would make the oxygen doubly positive, which is, right, you're starting to get to instability at that point. Okay. So kind of no matter what the heteroatom is, we only count one lone pair. What about this example? Let's look at a nitrogen that has a lone pair in a six-membered ring. Right? In this case, right, we don't need to draw no resonance needed to complete the cyclic conjugated system. Right? Every atom in this six-membered ring already is part of a pi bond. And so because there's no resonance needed, that means the lone pair does not participate in resonance. Right? You can't draw a resonance form of this ring where that lone pair is anywhere except for on the nitrogen, right? Or at least you can't draw a reasonable one, right? Um, and so we don't count that lone pair. So in this case, we look at this and we say, whoops, we say this one has 3 pi bonds. That's 6 pi electrons. That's aromatic. Okay? And so because the nitrogen is already a part of a pi bond there, we don't use the lone pair to create a new pi bond, so the lone pair doesn't count. So you do have to be a little bit careful with heteroatoms. It's not as simple as, oh, there's a nitrogen in there, it contributes a lone pair, we add 2 more electrons to it. Sometimes, yes. In the case of the 5-membered ring, that's what we did. But in the 6-membered ring, that's not the case. So we can also have examples like this compound is called imidazole. We can also have cases like this one where we have 2 different nitrogens. In one case, the lone pair contributes, right? So this lone pair is part of resonance. Right? This lone pair is not. Right? How do I know that? This nitrogen is already part of a double bond. We have a carbon-nitrogen double bond right here. Right? And so because that carbon-nitrogen double bond already exists, I don't need to use the lone pair to make that double bond. Right? And so that means this lone pair is not a part of resonance. This nitrogen does not have a double bond connected to it yet. It has only sigma bonds. And so in order to be a part of the conjugated system, in order to be a part of the pi electrons, we have to use this lone pair to make a pi bond and draw a different resonance structure. Or I guess we don't have to draw it, we just have to imagine it. And so we could draw it if we wanted to, right? We could draw the resonance form where it looks like this, right? And this would be, right now we have 2 pi bonds plus a lone pair over here. That counts as 6 pi electrons. So once again, you have 2 pi bonds plus 1 lone pair, 6 pi electrons. Imidazole is also an aromatic compound. But notice that it's an aromatic compound that has this nitrogen lone pair, which is not a part of resonance. And so if we were to look at these 2 lone pairs and say which of these lone pairs is more reactive, this lone pair is part of an aromatic system, and so it's very stable. Stable means unreactive. This lone pair is not part of an aromatic system, so this lone pair would be more reactive than the other one, right? The one that's not part of resonance. It doesn't have any other job, so it's going to be available to react with other things. So heterocycles or heteroatoms in aromatic systems, in general, I'll give you contribute a lone pair. There are examples where they don't, but those examples are always going to look like this, where it's a heteroatom that's already part of a double bond, right? And usually this is going to be a nitrogen. There's not a lot of other heteroatoms that can do this. So usually it'll be something like a nitrogen that already has part of a double bond. In that case, we don't count that lone pair as part of our aromatic system.